Assalamu alaikum. Here is Dr. Rabi Yasmin Khosa. I hope you guys will be safe and healthy. So our subject is lasers. This laser subject is for 8th semester of physics. Let's talk about it. So today we will study what does laser stand for, what is laser, basic concept of laser, population of atoms, and basic phenomena for laser. So these are our topics for today. What does laser stand for? This LASER. This laser is actually a combination of all these words. It is light amplification by stimulated emission of radiation. So laser is a combination of all that words. What is laser? Laser is a narrow beam of light of single wavelength in which each wave is in a phase with other near it. Okay, if I compare the laser light with the ordinary lamp, so we can clearly understand the definition of this laser. So we have a picture over here and we have distinguished all these things. So first thing over here, it is a direction. In our ordinary lamp, the light come up in all directions. You can see over here, but in case of laser, we have unidirectional light. And that, what does direction mean? It means that when the light come out from the lamp, it it is pretty far from each other, so they are not tightly at a low angle. But in case of laser, they are at a very low angle to each other. So therefore, these laser lights are very tight. In monochromaticity, what does it mean? It means that when a light come out, it can be of any wavelength. When we get a light from the bulb, may have you done experiment of prism in your ninth or eighth grade, because when you have a white light and if you put a white light in place of at the front of prism, then you get 7 colors. So it means our white light is made of 7 colors light, and each color has different wavelength. So therefore, in a bulb we get actually waves of different wavelength. But in a laser, we get a wave of single wavelength, therefore we call it monochromatic light. And what is coherence? Coherence means when these light come out, all have the same phase. And you can see in ordinary bulbs, all the lights have different phase, but in case of lasers, all the lights are on the same phase. Next is laser apparatus. Laser apparatus is a device that produces the intense, coherent, and highly parallel beam of coherent light. So this box, the box, this one, in this box we create a highly intense laser light. So this box we call it laser device. Basic concept of laser. For the basic concept of laser, we first have to see the atom and to see what kind of phenomena happens within that atom. So what is atom? Atom is composed of nucleus and electron cloud. If we see a picture over here, in this picture we have inside it's a nucleus and electrons are around it. So this is for electron and this is for the sign for the nucleus. And the electron in the atom, they are distributed in different levels, and we can give them a name: energy level E1, E2, or E3. So they are distributed in different energy levels. Basically, in atom, we observe two type of phenomena. One is excitation and the other is de-excitation. In excitation, the electrons from lower energy level it jump up to upper energy level. It is shown over here by this arrow. And when the atoms, when the electrons come up to the upper energy level, so it is over here for very short time. This state is unstable state, so it has to come back to its original position. So in de-excitation, it returns back to its original energy level and then it emits a photon. We call it de-excitation. So these processes we will study later, and they are very basic uh, phenomena of the atom, and they are very necessary for laser light to happen. Here we have population of atoms. Before to study in a detail about the phenomena of atoms, for example, excitation and de-excitation, we first have to know about the population of atom. Without knowing the population of atom, we can't explain all these phenomena. So what is population? It's the number of atoms per unit volume that occupy a given energy state. So for population, we first needed to know about the energy state. Always, first we have to fix the energy state and then we will find the number of atoms in it. It's basic example I can give you by this. For example, in Dera Ghazi Khan, there live 20 people, let's suppose. So this Dera Ghazi Khan is specific energy state and 20 people are the number of atoms. So we can say that population of Dera Ghazi Khan is 20. In atom, we have different types of energy levels. So what are these energy levels? Are energy state. It's a permitted orbit with specific amount of energy. If you see this figure in which we have, this is a nucleus, and around the nucleus we have different energy levels, and in each energy level different population of electrons exist, and these energy levels can be different two types basically. The first is ground state and the other is excited state. The ground state is the lowest energy level and all the other remaining are excited states. And every level has different energy level, and due to this different energy levels the population also depend on this energy levels, and it is shown over here in the form of bands. So this first band is the ground state and the all other above bands they tell us about the excited states, and in all these excited state and energy ground state the population will be different. I think it is clear to you. If you have any difficulty in understanding that population, you can come at me. I can repeat these things again and again. I have no problem. I just want you to understand it very clearly because this topic is a basic one. If all these things are not clear to you, then you will not be able to run this course smoothly. The population of energy levels we can find out by using Boltzmann equation. So what is this Boltzmann equation? It is m is equal to exponential minus E over kT. Here the T is energy level and the K is Boltzmann constant, T is temperature, and M is for population. So here we have a picture of two energy level system. This is first ground state, energy level E1. This is energy level E2. It has population N2, and this one E1 has population N1. So by using this Boltzmann equation, we can find out the population of different energy levels. And what does this Boltzmann equation tell us? If you see to this equation, you can see a clear exponential behavior between energy levels and population. And this equation tells that the population of energy levels, a population of atoms completely depend on energy levels and thermal energy. We discuss this later on the on next slide. Okay, so what is next? Here we have population in different energy levels. So by this Boltzmann equation, we can find out the population of this energy level E1 and population for that one energy level. So first we have this general Boltzmann equation, and if we want to find out the population for energy level E1, so what we have to do, just over here we have N1, this is population for energy level 1, and at the place of E, we will just put E1 over KT. And for the level E2, for this level E2, so what we will do, just we replace it with N2. This shows it's a population of level E2, and here it is exponential minus E2 over KT. So just we can find out the population of different energy levels by using this Boltzmann equation. So the Boltzmann shows that population is going to change with the energy level. Here we have relative population. What does relative population mean? It's a ratio of population N2 over N1 is called relative population. By relative population, actually we tell about the population of any energy level with respect to other energy level. Let's suppose here we have two energy level systems. This is energy level E1 and this is energy level E2. We can find out the population of either E2 energy level with respect to E1 or either the population of E1 with respect to E2. In a simple words, I can give you an example like that. For example, we are going to compare the population of Dera Ghazi Khan with the population of Multan. So this comparison is actually relative population. In physics, we mostly compare the population of higher energy level with respect to lower energy level, because we know that lower energy level will always have population, but in upper energy level the population is low or either they are empty. Therefore we say that in physics the ratio of N2 over N1 is called relative population. Okay, in a previous slide we find the population N2 and N1 by the Boltzmann equation. Just in this over here we have taken the ratio, and by taking the ratio we will get this equation. In other words, we can write down this equation like that, N2 is equal to N1 exponential minus del E over KT. So what is this del E? This del E is just energy difference of these two energy levels, E2 minus E1. Sorry. If you look to this equation, this relative population, you can see that this relative population depends on two factors. This relative population depends on two factors. What are these two factors? One is energy difference, E2 minus E1, and the other is temperature. So this is energy difference and the other is temperature. So this population, relative population depends on two things. Okay, if I can explain you, let me to take my pencil. Okay, let's suppose I have two energy level system. One is this energy level system and the other is this energy level system. Okay, wait a minute. Let me to take my pointer. Okay, I have a pointer. So this energy level system, over here the energy level are very far from each other, but in this energy level system these two levels are very close. So here the energy difference is very low, but here the energy difference is high. Okay, so by if and this equation tells, and here over the exponential we have a negative sign. So it means when the energy difference is high, then the relative population will be low. Okay, because these are so far, so we needed much more energy to transfer our electrons from this lower energy state to upper energy state, but here the difference is low, so they can easily transfer by using small amount of energy. They can jump from lower energy state to upper energy state, then the population can increase. So therefore when the difference is high, just as over here, when the difference is high, then the population will be low. And next is temperature. When we have high temperature, then by this temperature the electron can get easily energy from the ground state and can jump up to higher energy state. Okay, by increasing the temperature they can easily jump. Okay, but the thing is that when they are very close to each other, by just increasing a little bit temperature, and they have very low energy difference, so the population can increase on the upper energy level. So our conclusion is that at lower temperature, all the atoms are in ground state. So at low temperature, none of the electron in a ground state will have enough energy to excite to the upper energy state. So therefore, they will remain in their ground state. But as we increase the temperature, they move to the upper state because they get the energy. So by this energy, by kinetic energy, they can move to the upper state. But the thing is that the population will increase further if the difference of energy level is low. Okay, I think you have got that point. If you feel any difficulty, you can say to me. So here we have limiting cases about relative population. So this is again the equation of relative population over here, and now we see its limiting cases. So what is this limiting case? First limiting case is that if energy difference E2 minus E1 is almost zero, then what will happen to relative population? So just put over here in this equation, relative population equation, so this term will become 0. When this term is 0, then exponential 0 will be equal to 1. So then the population of N2 energy level will be equal to population of E1 energy level. So this is very rare stuff. We can have that in metal, because in a metal the energy levels overlap to each other, so the population of lower energy level can be up to the population of upper energy level. But in case of semiconductor and insulator, we can't get this condition. Therefore we are giving this name as a limiting case. And the next case is when the temperature is very high. When the temperature is high, if I place over T, replace with the infinity, so something over infinity, it is 0. So again we will get 1. So then we will again have population of N2 is equal to population of N1. So we can get the population at the upper energy level high if we increase temperature too much. So the conclusion is that as long as the temperature is in thermal equilibrium, the material is in thermal equilibrium, the population of higher energy state cannot exceed the population of lower energy state. So at room temperature and little bit above the room temperature, so the population of upper energy state can never exceed. But for the laser, to get the laser, we needed high population at upper energy level, and we call it population inversion. So I think we will talk about it in our second lecture, but right now it's important to you to know that at thermal equilibrium we can't get higher population at upper energy level. So at thermal equilibrium, always our ground state is full of population, but as energy level increases, the population decreases. Okay. On that slide, we have basic phenomena for laser. Okay. There are two basic phenomena for laser. The basic phenomena needed for laser actually. One is absorption and other is emission. So when this absorption happens, let's suppose we have two energy levels. One is E1 and another energy level is E2. When a photon come up and this photon has energy equal to this energy levels different, so this photon will be absorbed, and by absorbing this photon, the electron over here in this lower energy state, it will jump up to upper energy state. So this is absorption. And the next is emission. And when this emission happens, and here the electron is already at the excited state, so after spending a time over here in this excited state, this electron returns back to lower energy state. When this excited electron returns back to lower energy state, then it emits a photon. So this is emission process. Here the photon got absorbed, and in this process it is released. So we call it this one absorption and to this one emission. But these were the basic concept, and they were run for a long time. But in 1917, Einstein said that to attain thermal equilibrium, we can't accept only a simple emission that we have seen over here. He said that to attain a thermal equilibrium, we needed another emission process. So he divided the emission process into two types. So one is spontaneous emission, and this spontaneous emission is just simply this one emission, normal emission, and the other is stimulated emission. So this stimulated emission concept was given by Einstein, this guy, and this concept he gave in 1917. So let's study all these phenomena: absorption, spontaneous emission, and stimulated emission in a more detail on the next slide. Okay, get ready for that. Okay, the first phenomena is absorption. So here we have a figure of two energy level system. We have this lower energy level and this is upper energy level, and we have shown these energy levels energy with respect to this arrow. So this arrow is showing that upper energy level has high energy and this has low energy. Okay, we have a electron in this lower energy level. So a photon come up, and this photon has energy, and this energy is almost equal to the difference of these two energy levels. So when this photon comes, so this electron absorbs that electron and it will jump up to upper energy level. So the part of this figure is shows it is during the absorption. So this electron will absorb this photon and it will jump up to here. So this part shows that electron has come up to the upper energy level after absorbing the photon. Okay. So because this electron has absorbed the photon, so its energy has increased. So when its energy has increased, it can't live in a lower energy state. So it has to come up to the upper energy state. So it comes. Mathematically, this was physics explanation for the absorption. And we can explain all these phenomena with the help of math by just this simple equation. So what does it show? This A shows that this is some energy levels, either the electron, and then is absorbed h mu energy of photon. When this absorbs this energy of photon, then this energy level gets excited. This star shows that this energy level has got excited. So all that process we have summarized in this simple line in the form of math. Okay, now we can tell about the rate of absorption. So the rate of absorption is proportional to density of the photon and population of energy level E1. So this is population of energy level E1, and this will be population of energy level E2. Sorry, I forgot to mention over here, but we have discussed in a previous slide. I think you will find no difficulty in understanding. Okay, so the rate of absorption depends on energy of the photon and population of an energy level of E1. What does it mean? It means that the absorption rate will increase if the population in this level will be high. If there is no population, so how much will photon will come? No, neither a photon will be absorbed, and nor this electron will go up to upper energy level. So it's for absorption, it's really needed to have population in lower energy state. Okay, and the next is energy density of incident light. This means energy density of this photon. If this photon has very low energy, so this electron will never absorb it until this energy is equal to this energy level. So the rate of absorption depends on two basic things, and is proportional, and one is the population of energy level N1 and energy of incident photon. Without these two things, absorption will never happen. Okay, what is this BA2? This BA2 is the constant of proportionality, and we can call it Einstein coefficient for absorption. And this also tells us about the probability of transition from energy level of 1 to 2. This is energy level 1 and this is energy level 2, because by the absorption we get a transition from energy level of E1 to E2. Okay, I think it's clear to you guys now, and we can easily move to the next slide. Here we have spontaneous emission. So what is spontaneous emission? First, look to this figure. So again, we have two energy level system, and in this two energy level system, our electron is already excited to upper energy level. Okay, he is already excited to the upper energy level, and this upper energy level, this excited electron in upper energy level can never stay over here forever, because this excited state is unstable state. The electron will spend a little time over here, and after spending that time, it has to come back to the lower energy state. And this coming back to the lower energy state depends on two processes. One is spontaneous and other is stimulated. Here we are talking about spontaneous. So what happens in a spontaneous? Then this electron on this upper energy state, after spending a time, automatically come up to the lower energy state. So it will automatically will come up to the lower energy state. So this is figure for before photon emission, and this is figure after photon emission. So when it will come back to the lower energy state, so how much it has absorbed the energy, it will emit in the form of photon. So in In previous slide, we have absorption. It has absorbed the photon, and in this case, it is returning back the photon by coming back to lower energy state. So therefore, we get a photon, and this photon will have the energy exactly equal to the difference of these two energy levels. Okay, this was the physics explanation of this spontaneous emission, and we can write down all that process in the form of math. So what does it tell? It tells that here we have excited state. This star is telling about the excited state, and as the excited state come back to the ground state, then it emits photon. This H mu is telling us about the photon, and this is ground state. Okay, so this is spontaneous emission. We can find out the rate of spontaneous emission. So the rate of spontaneous emission is proportional. If I remove this equal sign and the constant, then it is actually proportional sign over here. So rate of spontaneous emission is proportional to N2. It means the population of upper energy level. So here the spontaneous emission only depends on the population of on that energy level. It doesn't depend on the population of level, ground level. So it only depends on the population of that level. And in absorption, we have seen that over there, the rate of absorption was depending on the intensity of incident photon. But in the case of spontaneous emission, no one photon come up during the emission, so therefore it does not depend on the intensity of incident photon. Okay, so it's only depend on the population of upper energy level. So therefore we have this equation. I think it is clear to you. If you feel difficulty, you can contact me. Okay, so it depends on population of, sorry, here should be upper energy, there is a mistake, it should be higher energy level. Okay, let me to remove, this is higher energy level. Okay, and this 821 is actually the constant of proportionality, and we call it Einstein coefficient of spontaneous emission, and this tells us about the probability of transition from level 2 to 1, because in spontaneous emission the electron comes from upper energy level to lower energy level. Therefore we call it probability of transition from level 2 to 1. Important features of spontaneous emission. Why this spontaneous emission? It is no outside controlled. So because I told you the excited electrons just automatically come up to the lower energy state after spending a time. So we can't control this from outside. And this is probabilistic in nature, same thing. And incoherent light come up. It means when it comes from upper energy state to lower energy state, it emits a photon. And this emitted photon can go in any direction. Okay, and 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 the emitted many photons can have different phase. So so the light emitted from here, it is just like the light of our simple bulbs. It is non-chromatic, same thing, and it's a lack of directionality. So it means this spontaneous emission is give a light just like our ordinary bulb. Again, we can see over here, if the light is coming out by spontaneous emission, then we will get a light like this. This is the superposition of jet light. They will they will do a like this. And here, this is bunch of waves over here of different wavelengths. So here can be the waves like this. It can be the combination of different waves of different wavelengths. And when these different waves of different wavelength will superimpose, then you will get a wave like that. So it will be random and it will be in all directions. So the spontaneous dominates in conventional light source. Here we have stimulated emission. For stimulated emission, here we have again two energy level system. So we can see over here in this two energy level system, our electron is already excited to the upper energy state. And so in this emission process, what happens that a photon come up. So when this photon comes, so this photon stimulates this excited electron to come up to lower energy state. So this coming photon is actually stimulating this excited electron to return back to its ground state. So therefore, we call it stimulated emission. In spontaneous one, the excited electron was just automatically coming down. There was no need of any stimulated photon. But here in stimulated emission, we needed some stimulated photon. So in this second part, the electron has come back to the ground state and it emitted a photon. So first is this stimulated photon, and the second photon is from this second photon is after the emission of after the excitation of electron to the ground state. So in this stimulated emission, we get two photons. One is the initial photon and the other one is stimulated photon. So by this stimulated emission, we can amplify number of photons. Okay, so all that process we can write down mathematically in this form. So there was already excited state, then a photon came up, and after the coming the photon, our state come to the ground state, and after coming to the ground state, we got two photons. Okay, and here is rate of stimulated emission, and the rate of stimulated emission is proportional to density of stimulated photon and the population of N2 energy level. So this stimulated emission will increase if the density of this coming electron increase. If here we get very low intensity photon, then this stimulated emission will not happen. So we needed a proper energy of this photon. Next, if there we have high population at this energy level, then too many stimulated emission will happen. If the population is very low, so stimulated emission will not happen. Then this this photon that is coming over here, instead of causing the emission, it will get absorbed if we have very high population in this lower energy level. Okay, so we don't want this electron to get absorbed, so we needed high population to upper energy level. And what is this B21? This B21 is constant of proportionality. We can call it Einstein coefficient for stimulated emission. And it tells us about the probability of transition from energy level of 2 to 1. And you have seen here that our electron returned from energy level of 2 to higher energy level to lower energy level. So it tells us about the probability of transition from level 2 to 1. Okay, here we have important features of stimulated emission. This is controllable from the outside. In a spontaneous emission, we can't control the process, but this one stimulated emission we can control from outside. Here the emitted photon propagates in the same direction as that of stimulated photon. Let's you can see over here in a figure, this is the electron. It was coming, and then after the stimulated emission, all the photons come up in a same direction. So therefore we get emitted photon propagates in the same direction as that of stimulated photon. So this stimulated emission is the only process by which we can get a laser, unidirectional laser, because in our spontaneous emission we get a light like a simple bulb. By this stimulated emission we can get a laser, and otherwise laser is not possible without this stimulated emission. Okay. So have exactly same frequency, phase, and the plane of polarization when they are going in the same direction and the same phase. So this is only possible in stimulated emission. Light produced is directional, coherent, and monochromatic. And the next thing is that this process is also responsible for amplification of light. Look, only one photon came enter into this system, and plenty of photon came out. So this stimulated emission is responsible for amplification of light. This is a process. I think that is enough for today. So see you next lecture. Take care. Allah Hafiz.